K-means forces every point into one cluster, even on a boundary. Scikit-learn's Gaussian mixture uses expectation maximization to return membership probabilities, and BIC helps decide how many components belong. You'll select a component count with BIC and return posterior memberships for a boundary point using a full covariance Gaussian mixture. I'm Professor Pi, teaching AI foundations with simple Python. Gaussian mixture models solve a common problem. You need to group data, but clusters might overlap or come in different shapes. Hard clustering gives a single label and hides uncertainty. A Gaussian mixture gives you a probability for each cluster, which matters when a point sits between groups, and you want to know how confident the model is. Think visually. Picture two blurry blobs on a scatterplot. Each blob is one Gaussian. The model learns a center and a spread for each blob. Then for any new point, it hands back probabilities instead of a binary decision. The payoff is soft assignments and flexible component shapes. The trade-off is you must pick the number of Gaussians and be careful with very small datasets. We will build a tiny demo that shows both soft membership and an automated way to pick the number of components with BIC. You will see a boundary point split across components and a repeatable selection for how many Gaussians to use. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Let us create the small toy dataset to make these ideas concrete. This snippet creates a small NumPy dataset with two visible groups in 2 dimensions. Before fitting any model, the viewer needs a concrete picture of what goes in. Each row of X is 1 point, and each column is 1 feature. The points are deliberately simple, with one group near 0 and one group near 5, so later probability outputs are easier to interpret. The center calculation is not clustering yet. It just gives one quick summary of the whole dataset. The visible output confirms the dataset size and its overall center, which anchors the rest of the tutorial. Now, fit a Gaussian mixture to capture those 2 blobs with full covariance. This example fits a scikit-learn Gaussian mixture model that can learn oval-shaped component geometry. K-means gives each point one hard label, but Gaussian mixture estimates a probability distribution for each component, including a mean and covariance. The parameter n components equals 2 tells the model how many Gaussian components to fit, while covariance type equals full lets each component learn its own full covariance matrix instead of being limited to a round shape. Random state equals 0 keeps the initialization reproducible for teaching. The visible output shows the learned component centers, which should line up with the 2 groups in X. Next, probe uncertainty by asking how a point in the middle is assigned. This code asks scikit-learn Gaussian mixture for soft membership instead of only a hard cluster label. The test array includes 1 point exactly between the 2 learned groups, plus 1 point near each group for later use. GMM predict proba test returns 1 probability per component for every test point, so a boundary point can show uncertainty directly. Order sorts the component columns by their learned X coordinate, making the displayed probabilities easier to read from left group to right group. The visible output shows that the middle point is split across components, which is the key advantage over a forced hard label. But we should not trust a fixed choice of component count without checking alternatives, so compare models by BIC. This snippet uses scikit-learn Gaussian mixture BIC to choose a component count instead of guessing by eye. A model with too few components can merge real groups, while a model with too many components can spend extra parameters explaining small details. The loop fits one Gaussian mixture for each candidate K and stores its BIC score in scores. Because lower BIC is preferred, min scores key to scores.get selects the component count with the smallest score. The visible output shows the selected count, turning model choice into a repeatable comparison rather than a hard-coded assumption. Now build the final baseline that picks the best K and reports posterior memberships for our test points. This example combines the earlier pieces into a compact scikit-learn Gaussian mixture baseline. Final uses the BIC selected best K, fits on X, and then calls predict proba on the same test points from the soft membership step. Instead of printing only labels, report pairs, each most likely component with its highest posterior probability, so uncertain boundary cases stay visible. The sorted order keeps component numbering aligned from left to right, which makes the report easier to explain on screen. The visible output shows both assignments and confidence, giving a small but complete clustering result. In a real workflow, you would map this to a customer segmentation or sensor grouping task where overlap matters. The same pattern scales. Pick candidate component counts, compare with BIC, then inspect posterior probabilities for ambiguous users or readings. That helps you decide whether to act or to ask for more data. Quick summary. Gaussian mixture fits soft, probabilistic clusters with means and covariances. Use it when clusters can overlap or have different shapes and you want uncertainty for each point. Watch the number of components because model selection matters and small data can mislead BIC. For one practical next step, expand the BIC search range and compare covariance type full with covariance type diag to see how much shape flexibility actually helps on your dataset. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.